Okay, class, we're about to start section 312, and we are going to do the problems are supposed to be from problems 1 through 11 odd on pages 373 to 376. I'm going to do problems 3, 7, and 11, and if you have any additional questions, feel free to ask me that via email, and I will gladly go over those problems with you. Okay, so starting with number 3 on page 374, it says in 1990, the International Panel on Climate Change projected the following future amounts of carbon dioxide in parts per million or ppm in the atmosphere. So they have the years and amount of carbon dioxide in the table. It says, A, use your graphing calculator to create a scatter plot of the data. Let T represent the number of years since 1990, and A of T represent the amount of carbon dioxide in, what was that, parts per million in the atmosphere. Do the carbon dioxide levels appear to be growing exponentially? Okay, so what we need to do, and let me draw this table here. So we have here, we have the year, and I'm just going to put amount because this is in your textbook. So we had 1990, 2000, 2075, 2175, and 2275. So we had 353, 375, 590, 1090, and 2000. Okay, now this is our table, and they tell us in the directions that we want years since 1990. So what we have to do first is convert these years to represent since 1990. So this would be our 0 year. This here would be 10 years. This here from 1990 would be, what's that, 85 years. And then from 2185, that'll be 185 years. And then 2275 would be 285 years. Okay, so now, one other thing they told us is that we're going to work with T and A of T. So basically, this here would be your T, these values here since 1990, and A of T would be the amount. And we know A of T really is your Y value and T is really your X value. So we go over here to this table because we want to see what this graph looks like. So we would add a table and we would type in these numbers. So we would have 0, 0, then 10, 85, 185, and 285. All right. Then we would have 353, 375, 590, 1090, and also 2000. Now, what I could do, I could zero this in, I could zoom in. And as you see here with me zooming in, maybe if I expand this a little bit, yeah, it's hard for us to see. So
if you press the little like magnifying glass in the corner thing, it zooms in for you. Over in the left, below your little chart, there, like right. Yep. If you press that, it'll.
Oh, okay, thank you. All right.
You're welcome.
So now we have the magnifying glass, and as you see here, it looks like it's growing exponentially because it's doing the curve here. So we can assume with problem 3A, because they asked us, do the carbon dioxide levels appear to be growing exponentially? And I would say yes, because of it looks like an exponential curve here. Okay, now we go to 3B. It says use your graphing calculator to determine the regression equation of an exponential model that best fits the data. Now, first of all, before you're able to do the regression model, you have to know what the regression model is, the general formula. The general formula for the exponential regression is y equals ab to the x power. So when we go over here, now I know we're supposed to be using a and t, but we're going to get back to that once we put this in here and get our equation. So we will have y1 because our y values here is in y1. We will go here to the keyboard to the ABC and hit the tilde, and we'll do AB, and then we want to take that, we'll hit the AB power, we would take that to the x1 power. Now, this right here encompasses all of these values. Now remember, in one of your projects, you were supposed to click the log mode box. The log mode box comes up when you do exponential regression. So you have to click here, and now it will give you the equations. Now, if you notice here, you have your A and your B here. But if you notice here, we have our correlation coefficient. And remember, the graph is exact when your correlation coefficient equals 1 or -1. And if you notice here, our correlation coefficient equals 1. So that means that this equation is actually exact. It's not an estimate. So we know that y, for the purposes of this problem, is really a of t. So we'll write a of t is equal to, now they tell us what a is equal to. And they tell us to, well, they didn't tell us to round this, but we'll round to 2 decimal places. So a would be 352.65. Now b we're going to round to 3 decimal places. It'll be 1.006. And then remember, our x is actually t. So this right here would be our equation. Now we go here to C. It says use the model in part B to determine in what year the 1990 carbon dioxide level is expected to double. So they want to know what year that this is going to double. So what we could do first, we have to go to 1990 and see how much it is presently. It has it at 353. So, well, they said according to the model. Okay, let me backtrack here. Since they said according to the model, we're not looking at the table now. We're supposed to look at what we have here. Now, they said according to the model, this number here, this A represents the y-intercept. So they're telling us to take this value here and double it. So we'll take the 352.65 and multiply by 2. So what we want to find out is what year would this equation equal 705.3. So we would take this equation and we will put 705.3. We will put that in place of A of t and set it equal to 352.65 times 1.006 to the t power. Okay. Now, remember, t represents our years since 1990. So we have to get t by itself. So the first order of business, we'll divide each side by 352.65. Now, when we divide these two here, that would give us 2. Because remember, this is double this number. So we know when we divide it, it will give us 2. And we will have equals to 1.006 to the t power. Now, this is where some of our, how should we say, this is where some of our log rules will come into play. Now we can use natural log or we can use regular log. It really doesn't matter which one that you choose to use, but you do need to use one of them. So I'm going to do log. So, because we want to get t by itself, so I would do log of 2 is equal to log of 1.006 to the t power. Now remember, one reason why we could put a log on both sides is based on the golden rule of algebra, which states that what you do to one side, you have to do to the other side. So now, with this t according to the log rules, this exponent of t could come out in front of the log as multiplication. So now we would divide each side by log with the argument of 1.006 on both sides. And now we're going to end up with approximate value equal to t. So we could put this in our calculator. So we would have, we'll go to functions, go to miscellaneous, and we have log, and then it'll be log 2, close that parenthesis, hit our division sign, and then log 1.006. And close our parenthesis. Now, if we round this, let's just say we round it to the nearest year. So if we round it to the nearest year, it'd be approximately 116. So it'd be 116 years after 1990. So basically you could say in 2106, the carbon dioxide levels is expected to double. Does everyone follow that? Now, they asked us, oh, did you all have a question?
No, no, I was saying yes, I follow what you're saying.
Oh, okay, no problem, no problem. Okay, now it says here for D, it says verify your result in part C graphically. Okay, so basically, we're saying X is equal to about 116. So we have this graph here. We could type in, and I believe that we could do this on here because I'm used to doing this on the TI calculator. We have X is equal to 116. And when we have X at 116, if you notice here, it's approximately the value. It's a little bit above it, but we're basically there because we rounded this. But if we didn't round it and just put 115.87, let's just show that. If we put 115.87, 07, let's see, 58146. We put that there and click here. You notice here it basically gives us, well, actually it rounds it. Okay, so it's going to round it regardless, but it gives us something very close. Now this is one way of doing it since we're doing it on Desmos. Another way of doing it is this here. Since our equation would be, since we already have our line here, or our graph, we could theoretically put y is equal to 116. And if you go here, well, actually, no, that wouldn't work. Hold on 1 second. Okay, class, I made a little mistake by putting the y is equal to 116. I actually was supposed to set y equal to the doubled amount, which was that 705.3. Now, when you put y equals 705.3, if you click here, you would basically have it, you would basically get the answer. So class, after we type in the y equals 705.3, when we look at the intersection point here, you notice that the x value is actually off. So what you're supposed to do is to type in the equation that you got before. You know that a of t is equal to 352.65 and then times 1.006 to the t. So you'll do y is equal to 352.65, and then you would do the parenthesis 1.006, and you would take it to the x power. Now, the reason why we had to type this equation in is because when we're up here using this graph, this is the graph that has been graphed originally. So when we got the 705.3 and we got 113 point something, that was more exact than what we have here. Remember, the equation that we end up using, that was an approximation from the exponential regression that we had, because remember, we rounded. So when we typed in our rounded equation, had both the doubled answer and the rounded equation. When we click here, is more close to what we have, that 115.87, and if we round that, that'll be 1. So that's closer to what we have here. And this is how you would do it graphically. You would set y equals to the double value, and then y equals to the equation, the rounded equation that you had. And then it will give you basically the same answer. Okay, so now that took care of problem number 3. Now we need to move on to problem number 7 was our next problem. Problem number 7, we had e to the 0.05 t power equals 2. And the directions state, in exercises 4 through 9, solve each equation using the algebraic approach. Verify your answers graphically. So basically, we're going to do somewhat of the same thing we did in the previous problem. We're going to use the logs and natural logs on both sides to help us solve this problem. Now, since we have e to some power, it would make more sense for us to use natural log. And I will show you why. So we had a natural log of e to the 0.05 t power is equal to the natural log of 2. Now, natural log and e will simplify each other out and leave you 0.05 t is equal to the natural log of 2. That's why we use natural log, because it will simplify out with the e. Now we divide each side by 0.05. And then we have t be approximately 13.86. Now we could check it in our calculator just to be sure. So we'll go to functions, then miscellaneous, we'll take natural log and we'll put 2 and then close that parenthesis and press divided by, and it'll be 0.05. And it gives us 13.86 when we round it. Okay, so now our last problem of the night will be problem number 11, and it's broken up into 4 parts. So we have 11A. It says here, and this is at the bottom of page 375. It says in 1969, a report written by the National Academy of Sciences, U.S., estimated that Earth could reasonably support a maximum world population of 10 billion. The world's population was approximately 3.6 billion and growing continuously at 2% per year. If this growth rate remained constant, In what year would the world population reach 10 billion, referred to as Earth's carrying capacity? Use the model. Let me write this model down. P is equal to P naught e to the kt. Okay, so now we move over to the next page. It tells us here where P is the population in billions, P naught is 3.6, K is 0.02, and T is the number of years since 1969. So let's do this. Let's substitute in for the P naught, which is 3.6, and then also the K, which is 0.02. So now we have this formula. P is equal to 3.6 times e to the 0.02t. Now we're going to substitute because remember, P stands for the population in billions, and we said Earth's carrying capacity is 10 billion. So that would be 10 is equal to 3.6 e to the 0.02 t power. Okay, so now the first thing we would do here is divide each side by 3.6 because we're trying to get t by itself. So 10 over 3.6 is equal to e to the 0.022t. Now remember, we're trying to get t by itself, so we'll take the natural log of both sides, so we could get rid of that e. So we had a natural log of 10 over 3.6. Natural log in e will simplify out, and you have 0.02t. We divide each side by 0.02, and we're going to put this in the calculator. So we had a natural log of 10 divided by 3.6. Close that parenthesis. Then we will hit our division. And then that'll be divided by 0.02. And then that will give us approximately, if we round to the nearest year, it gives approximately 51 years. So what we would do here, we would take 1969 plus 51 should be 2020. Okay. Now we move on here to B. It says, according to your growth model, when would this 1969 population double? Okay, so first of all, we will look at what the population was in 1969 as far as the model is concerned. Now the model, basically, we would have, so basically if we take our original model, which we had that formula, which was P, and this is actually B. We had P is equal to 3.6 e to the 0.02t. Now, according to this model, 3.6 would be our starting year, which would be since 1969. So to double that, it'll be 7.2. So it'd be 7.2 equals 3.6 e to the 0.02t power. We divide each side by 3.6. So this would be 2 is equal to e to the 0.02t power. Now, we take the natural log of both sides. We know on this side, the natural log in the e will simplify out and leave us 0.02t. We divide each side by 0.02. So we'll take the natural log. Matter of fact, we could just change this bottom number here from the 5 to a 2. We had a natural log of 2 divided by 0.02, which is approximately 34.7. So we would say that this will be sometime in 2003. Because if you add 37.7 to 1969, that'll be about 2003, sometime near the end of 2003. So now we go to C. It says the world population in 1995 was approximately 5.7 billion. How does this compare with the population predicted by your growth model in part A? Okay, so let's first do this. We would take 1995 minus 1969, which would be 26 years. Because remember, this model is since 1969. So we're dealing with T being 26. So we'll take the population 26 years later from 1969 is equal to 3.6 times e to the 0.02 times 26. When you put this in your calculator, you'll get 6.06, and this will be in billions. Now, they want us to compare this, the actual population was approximately 360 million below the prediction. Now, approximately 360 million below the prediction. Okay, because remember, they gave it to us in the directions when it said that the population was approximately 5.7 billion, but we were supposed to come out with 6.06 billion. So that's approximately 360 million below the prediction. Now we come to the last part of problem 11, which is D. It says here the growth rate in 1995 was 1.5%. Assuming this growth rate remains constant, determine when Earth's carrying capacity will be reached. Use the model P equals P naught e to the KT. Now remember, K is basically telling you your percent, your growth rate, and that's written in decimal form. So basically, you have P is equal to P naught will be 5.7 because that's how much it was in 1995, 5.7 billion. And that was from our previous problem C. Then we would have E, and our K would be that 1.5%, which written as a decimal is 0.015. And then that'll be times T.
I'm
Now,
sorry, where did the 5.7 come from?
if you look back up at C, okay, you see.
Oh, okay, in their word problem. Okay, I see
Right.
it now.
You see it. Okay,
Okay.
great. Okay, so now, oh, and just for people looking at this video, if you look at the first sentence of C, it's 5.7 billion at the end of the first sentence in C. That's where we got this 5.7 from, because we're doing it now since 1995. Okay, so now they tell us that they want Earth's carrying capacity. We were told earlier that Earth's carrying capacity was 10 billion. So this P would become 10. So now we go through and solve for T. Divide each side by 5.7. So it'd be 10 over 5.7 is equal to e to the 0.0115t. we'll take the natural log of both sides. So this natural log in E will simplify out. So you have natural log of 10 over 5.7 is equal to 0.015 t. Divide each side by 0.015. And when you put this in your calculator, this will be about 37.5. Now, if you add this to 1995, the year would be 2032. That would be the year that Earth will reach its carrying capacity. Now, are there any questions? Okay, so we're done with actually 3.12, and so we're done with chapter 3. So now that means that you should be ready to take your exam, and I will take any questions you all may have. So please email me if you have any questions. Have a great day.